Good day, viewers. Here, welcome to my channel. Today's topic is looking at solubility product constant. Most substances are soluble in water, but the degree of solubility differs widely. So when a solid that is sparingly soluble in water is introduced into water, a certain amount of that solid dissolves, while the rest remain undissolved. So what it means that equilibrium will exist between the solid, undissolved solid, and the ions in solution. Okay, look at this salt. So salts that are, we'll say, insoluble, that cannot dissolve, that's insoluble in water or does not dissolve in water. All those salts, they can dissolve in water to an extent. Okay, look at this salt, barium peroxide sulfate 6, silver chloride. There are so many of them. So you know that all the salts of sodium, potassium salts are soluble in water. Okay, so look at this. This solid. We consider this salt to be insoluble, but it can dissolve to an extent in water. So these are ions. Barium sulfate. Barium is in group 2 element, so the charge, the valency is 2. So 2 plus 2 minus. So there's no charge here. You must know how to write this equation. Very important. So this is the solution. The solution, this crystallization. Okay. So you can see the equilibrium that exists between this and the ions in solution. So the equilibrium constant for solubility products that exists between the solid and the ions in solution is what we call solubility product constant. So use the symbol as KSP or solubility constant. So let's write equilibrium. Let's apply the law of mass action. Applying the law of mass action to this. So K is equals to concentration of barium ion times that of sulfate ion divided by that of the reactant, which is barium sulfate. So look at this. The concentration of pure solid by convention is assigned 1 because the concentration of this pure solid is independent of the amount of solid that is present. So assign 1. So this is 1. It's assigned concentration of barium ion, sulfate ion divided by 1, which will still give you the numerator. So this is 1. So it will not be so you will not put the solid, you won't put the concentration of that solid. So this is how to write it. So what it means that solubility product constant is the product of the molar concentration of the ions raised to the power of the stoichiometric coefficient in a balanced equation. So which means equation must be balanced. The equation must be balanced. All right. Look at this question. Write the solubility product constant for the following. By the time we are through with this, you should be able to write any question given to you based on something like this. You don't have to write it. Okay, let's start with question number 1. So zinc sulfide. So solid. So put the equilibrium reversible sign. So what's the charge of zinc? 2 plus is aqueous. So it's ion. Then this sulfide ion. So you put 2 minus. 2 plus 2 minus. That's 0. Put aqueous. So the solubility product constant is going to be what? Put KSP is equals to, of course, concentration of the what? Of this product. Since this one is 1, solid is 1. So this one will not appear. So put it times, not plus, so times. So this is it. Silver chloride, solid. So silver ion is plus. Chloride ion is also what? Minus 1. So KSP for this will be equals to concentration of silver ion times that of chloride ion. So I'm going to write for lead 2 chloride. So you put it solid, put your reversible sign. So what's this lead 2? When you see this chlorine, valence of chlorine is 1. So it means that this 2 is the valency for lead. Because I'm not seeing any 1, chlorine is 1, that's 1, invisible 1 here. So 2 plus good. Chloride ion is minus. But I have 2 atoms of chlorine here, 2 atoms. So we put it here as coefficient, not here as subscript. We put it in front here as coefficient to balance it. So 2, this is 2 minus. 2 minus 2 plus is equal to 0. There's no charge on this compound. I did a video on how to write ionic equation. Watch that video, can also help you on how to write ionic equation. Okay, so put aqueous. So I'm going to write the KSP. So KSP, concentration of lead 2 chloride times that of. So remember, we said that raise to the power the coefficient, raise to the power coefficient. So the coefficient of this one is 2. You raise it to the power of the coefficient. So the fourth one I'm going to do like this. Okay, let me put it there at once. So for this one, so it's going to be, look at this magnesium. What's the charge for magnesium? When you see chemical reaction of chemical formula, those elements that already could interchange their valencies. So this 2 is the valency of magnesium. This 3 is the valency of this tetraphosphate 5 ion. This is the charge. So magnesium, the valency is 2 plus. If you know the group that element belongs to, that's also what the valency for it. So look at this 2 plus. But I have 3 atoms of magnesium plus PO4. So what's the charge? The charge is 3 minus. 3 minus. How many atoms do I have? You can see this is I have 2 atoms of PO4. So put it as coefficient. So what would be the KSP? KSP for that is going to be what? Concentration of magnesium ion raised to power. The coefficient is what? 3. Raised to power coefficient, which is 3. Times concentration of PO4 3 minus raised to power. The coefficient is what? 2. So let's do the same for this. You don't need to be scared. Just break into ions. So calcium ion is 2 plus. Aqueous. Ammonium ion. Of course, now ammonium ion is plus. Phosphate ion. PO4 3 minus. Aqueous. So 2 plus 1, that's 3, plus 3. Plus 3 minus 3 is 0. So it means correct. There's no charge on this compound. There's no charge on that salt. So we're going to write the solubility product constant for that. So KSP. So case subscript SP will be Ca2 plus times the ammonium ion concentration and PO43 minus. So this is KSP for that. So the last one is chromium 3 hydroxide. Chromium 3 hydroxide. So it's the last one. Cr. So this solid. So look at this. Hydroxide ion is OH minus. OH minus. OH minus. So this thing 3 I see here is for chromium. So chromium is 3 plus. Hydroxide ion is OH minus. But I need to balance the atom of hydroxide ion. So that's put 3 here to balance the atom. So 3 plus 3 times minus. 3 plus 3 minus. So KSP is concentration of chromium 3 ion times that of hydroxide ion raised to the power coefficient, which is 3. Okay. So this is very simple. So I know that with what I've done on the bond, you can be able to write anyone that's given to you. Let us look at this question. What are the ionic compounds whose solubility product expression are? So you can see this, you see this one, you see. So we have to write the compound, ionic compound. Okay, look at this, starting with number 1. So this bismuth, the charge is 3 plus. And this one, the charge is what? 2 minus. Let us write the chemical formula of this by interchanging their valency. So these two, is going to this two is going to what? Going to be bismuth as subscript. So the sulfide ion, look at this. You're going to interchange this valency for these 3. So put the 3 here. So this is the compound, ionic compound that produces. If you want to write it, look at it, how it's going to be. If you put it like this. So look at this. This charge is 3 plus. Then how many atoms do I have here? I have 2. Sulfide ion is 2 minus. That will show you that this charge has interchanged their valency. So how many atoms do I have? I have 3. 3 atoms. So when you're writing the solubility product constant, if you put this Bi3 plus, the coefficient raised to the power 2. The same thing. S2 minus raised to the power what? The coefficient which is 3. Alright. So without wasting time, so we're going to write the compound that form this. This is zinc. So what the charge for zinc is 2. So hydroxide ion, the charge is minus, that is 1. So it means that atom will be here. The same thing as 1, the same thing as nothing. Then OH. The charge on zinc is going to do an exchange it, and this is a radical. Use what? Parentheses to enclose it. So put the 2. So this is the compound that. So seeing this is 2 plus, this 2 minus. So what it means that they are the same thing. 2, 2, it will cancel out. So for this one, it's going to be like this. Because the valencies are the same, 2, 2, so it will cancel out. So look at this. Silver ion is 1. This one is 2 minus. So there will be exchange of what valency? So Ag2. So CO3. Because this one is 1, so there's no point in closing it in parentheses. So this is how to do it. I have a practice question for you based on the last exercise that I did. So what is the ionic compound whose solubility product expression is this? So post your answer on the comment section. Okay, so I want you to note that this solubility product expression is only valid for slightly soluble compounds or slightly soluble salts. not for quite soluble or moderately what soluble salt, just for only what slightly or sparingly soluble salt. So post your answer on the comment section. So next video I'll be uploading will be on calculation of solubility product constant from molar concentration. Thank you for watching and do have a great day. Bye.